Hello people interested in the shape of the Earth. In this video, I'd like to focus on the horizon and bring to the discussion the process of image formation. Do we all talk about the same thing when we say horizon? Far from it. Each of us has both a theoretically and empirically different horizon. Here is my take. For a particular observation point, the horizon line is not a fixed landmark, but depends on the optical device that generates it. Regardless of situation, obstruction of the lower part of objects in the distance will always be observed. Even if Earth were a sphere, the horizon observed on the sea would not be due to the curve of the Earth. I hope I can explain this position in the following slides. First, a reminder of how images are formed in any optical device. Eye, camera or simple camera obscura, drawn here for simplicity. In all cases, light reflected by objects passes through a narrow opening and forms an inverted small image on the sensor screen. The vast differences between optical devices result from the details of the individual components, lenses, aperture and distance to the sensor, and the resolution of the sensor screen. Now, what happens to points on the lowest surface in the field of view when we look parallel to the ground? At a close distance to the aperture, they will be projected at the top of the screen, away from the horizontal line. As the distance increases, these points approach more and more the horizontal line on the screen. Here is a hypothetical example. Imagine that there is a line of oil patches floating on the sea. Viewed from the side, they are all equal in size and equidistant, and they stretch from the point 0 to infinity. How will they be observed when the camera faces them? In the drawing, I left out the camera for simplicity, but you can see the point where the light rays intersect. The first patches will be clearly separated in the formed image, as they are well away from the horizontal line of sight. However, with increased distance, not only do they become smaller, but they start overlapping as they approach the horizontal line. I think we can all agree that it is impossible to ever be able to observe all patches all the way to infinity. Where is the point where we lose them? Well, that is why I said it all depends on the optical device. For example, it is easy to understand that the better resolution power will make possible to separate two patches that seemed fused. Also, different focal length, lenses and aperture will greatly influence the number of patches that form on the sensor screen. So, I would like to claim that this line we call horizon is different for all of us. The reason we all refer to it as a unified concept is that this line always appears in any optical device as a result of the image formation. Horizon is in fact the eye level. Let's assume that in this particular case we determine that a certain number of patches can be well distinguished in the picture, and the last one is situated at angle alpha to the line of sight. This means that any patch for which the angle is smaller than alpha will disappear. Bearing this in mind, let's see what happens to a tower in the distance. In this hypothetical situation, we maintain the exact same conditions as in the previous slide, but instead of oil patches, we observe a lighthouse tower on a hill. We can use the angle alpha we found to predict what will be visible on the screen. As we saw, beyond this angle, objects disappear. We can speculate that what happened below the line of sight applies also above. This means that the lower part of the tower will be invisible, and this obstructed part will increase if the tower is farther away. I think the confusion in this area comes from the assumption that perspective simply shrinks objects and thus they can only disappear whole, not in parts. This is true for small objects before angle alpha. However, large objects such as towers or mountains can be situated at a distance where their top is above the critical angle, while the bottom is engulfed in the line of sight infinity problem. This is all due to the way the images form, by crossing rays of light, not by accurately keeping them parallel, as we are misled to believe when we look at representations from the side. So now, how does this apply to the curvature problem? For a flat surface, we can find the critical angle alpha as I just explained. For a curved surface, we might find a larger angle beta, but only if the curve is significant for that case. If the curve is very slight, it is easy to imagine that the angles will be equal. An example where everybody agrees the curve of the Earth plays no role is when we lie on the ground and observe a flat field. There are some nice videos on this. Please look for the links in the description. If the curve is significant, what we will notice in the lighthouse example is the disappearance of more of the lower part than expected for the flat case. To emphasize again, the obstruction of the lower part will always happen below a critical angle for both flat and curved surfaces. But this obstruction will be larger in the curved scenario. There are lots of curvature calculators on the internet, such as this one at debunks. The problem I see in all these calculators is the usage of the term horizon. As I hope I convinced you, the horizon is a volatile term. The drawing assumes the only reason for obstruction is the curve, while this is definitely not the case when viewer height h is very small. If we place the camera 10 centimeters above the ground, the calculator predicts a distance to the horizon of 1.13 kilometers, without any knowledge of all the optical details of the observer. In my oil patch example, do you think you can observe from 10 centimeter height the same number of patches if you use just the naked eye or a P900? If not, which is the real horizon? Which optical device gives exactly 1.13 kilometers? To me, these calculators are strictly geometrical, not a prediction of what can be seen, because the image formation is not taken into account. Let's examine an example from Wikipedia. If all I presented so far was taken into account, we would have a detailed comparison of a flat versus curved model. Instead, we know nothing about the optical device used and not even the predicted geometrical obstruction. The tacit assumption is that on a flat surface, using this particular device at this particular location, we would obtain an image in which the base of those buildings would be completely visible. Unfortunately, we cannot build a corresponding flat model with the exact distances involved. So the debate will continue till people realize they have to consider the optics. To make matters worse, bodies of water are never so calm as to have zero ridges. Due to perspective, a wave close by is equal to a small hill in the distance, so it can easily obstruct objects that would be otherwise visible. Also, atmospheric conditions introduce further complications. Before concluding, I would like to propose a hypothetical experiment. Given two towers at the sea level, we make observations of each from the base of the other. Then we find another observation point that can be higher than sea level in order to obtain both towers completely visible. On this image, we draw a straight line to connect the lowest points visible from each other's bases. We compare this line to that of the horizon. If these two lines are parallel, it means that the obstruction observed from each other's bases is not due to curvature, but to other causes. If curvature is the reason for obstruction, the horizon should be observed to curve slightly and touch the straight line. To conclude, horizon can be a mysterious concept if the principles of image formation are not taken into account. The horizon is different for each optical device and observation point. Obstruction of the lower part of objects will always be observed, even on a flat surface. Even if Earth were a sphere, the horizon observed on the sea would not necessarily be due to the curve of the Earth. Thanks for watching. Please let me know what you think.